Hello, I'm Nicholas Andrews. This talk is Learning Invariant Representations of Social Media Users. My co-author is Marcus Bishop. We're both from Johns Hopkins University. The problem we consider in this work is how to compare users on social media. Here I'm showing two sets of documents by two different users, Boris and definitely not Boris, and you may wonder based on these usernames whether or not they are in fact composed by the same underlying author. So to talk about this a little more precisely, we'll introduce a term called an episode, which simply stands for a small collection of short documents, each with text and accompanying metadata, like timestamps, and composed contiguously by the same user, such as Boris or definitely not Boris above. So in general, comparing users on social media is difficult, and I wanted to list just a few of the challenges. The first, and maybe the most pertinent, is non-stationarity, which is simply that participants and topics evolve over time in response to events in the world. And retraining models or annotating new data to account for this may not be practical. Another one is sparsity. This is just that a single tweet may not contain enough content to establish who wrote it. Another issue is simply the scale, the number of users that are active at any given point in time on a platform like Reddit. So what's been done before? There's a fair amount of prior work in what I'll call authorship classification. I won't go through each of these papers in detail now. Please refer to the paper for that, where we discuss these in length. But I'll point out some common patterns. Essentially, much prior work is focused on the closed world setting, where the authors seen at training time are the same as the authors at test time. What we're doing differently in this work is to expand this to the open world setting, where new authors may appear at test time that we haven't seen at training time. And to handle this setting, we need to learn to compare episodes by any author, not just those that we've seen before. The other difference is that we're going to be scaling up the number of authors substantially. As we'll see in the experiments later, we'll go up to several orders of magnitude more authors than are considered in prior work. So our approach in a nutshell looks like this. We're going to be taking episodes and projecting them using a learned embedding, which you may not be surprised to hear is a neural network, into a fixed dimensional vector space. And once in this vector space, we can easily compare episodes according to how similar the underlying vectors are, using metrics like Euclidean distance or cosine distance. So having given the general idea, it remains to say something about the architecture of the neural network we use, and then the loss that we use to fit its parameters. So before going into more detail about the architecture and the loss, I'd first like to give a general impression of the procedure we use to train the embeddings. So it's a fairly simple idea. Essentially, we use a dataset that gives us histories of user activity. That is simply just what comments each user posts. And we use this history to learn invariant user features. So what do we mean by invariant user features? Well, these are simply those that are consistently predictive of authorship over the entire history that we consider at training time. So just to illustrate this, to train the model, what we're going to be doing is subsampling episodes from the history we have from each user. So if we consider two users, Alice and Bob, in the first epoch, we might sample 2 episodes, and here the red boxes each comment in an episode. So here we're looking at episodes of length 16, just for illustration. And in the second epoch, we sample 2 different episodes, and this happens uniformly at random, which means that these episodes may or may not overlap with previously used episodes. And what we're trying to do here essentially is to help the model learn which features don't change over time and which do. And those that don't, those that are consistently predictive, are those which are invariant. So crucially, we're not handcrafting these features. That's the magic of neural nets. And to give you maybe a better sense of what these features are, if you're familiar with computer vision, an invariant feature there may be something like the shape of an object, but things like lighting and orientation we would want to learn to ignore, essentially. So having given the general impression of the training procedure, I want to give a little more detail about the architecture, though I will preface this by saying that we think this is the least interesting aspect of the work. So just walking through this quickly, we encode each document using a subword tokenizer. For each document, we then apply 1D convolutions of different widths. This is a fairly standard architecture, I think originally proposed by Kim in 2014. We then apply max over time pooling. This essentially reduces each document, each comment or tweet, to a fixed length vector, fixed dimensional vector. We then combine these document vectors along with any associated metadata across the entire episode using a self-attention mechanism similar to the encoder part of the transformer. Please see the citation below. And finally, we apply a batch-normalized multilayer perceptron to project this to our target embedding size D. So to show this in a slightly more visual fashion, here's something roughly analogous to a computation graph for the architecture. I'll point out two things here. The first is just that, again, we're reducing the length of each comment, the text of each comment, to a fixed dimensional feature vector before combining it with the metadata. And then the second is that we actually use several layers of self-attention, which is, again, similar to how it's done in the transformer. We also pool each layer of attention separately before concatenating them and projecting them to the final embedding using the multilayer perceptron. So having said something about the architecture, I'll now talk about the losses we use to train it. So we looked at two losses, both of which can be thought of as surrogate metric learning objectives, meaning that they both, as a byproduct of optimizing them, accomplish something like metric learning, but are easier to actually optimize than exact metric learning would be. So the first is a standard softmax loss. So this is probably familiar to most of you, but essentially consists of projecting the embeddings via a linear projection down to the number of classes we have, where each class is a different author that we have in our training data. You'll note here there's no bias, which is deliberate. Then we apply a softmax. This is simply to compute the classification error. When we're done training, we discard W and just keep the embedding portion that preceded. So the second loss we looked at, which comes from the vision community, is an angular margin loss, and it's called arcface in the original paper. So what's nice about this is that it enforces a margin between classes, and this has the dual effect of encouraging intra-class compactness, which was achieved by the softmax loss, but then in addition also inter-class separation, meaning that different classes are far apart, and that's the purpose of the margin. And just to point out one more thing about the angular margin loss, which is that we normalize the embeddings before computing the loss, and so when using this loss to train the model, we compare embeddings using the cosine distance rather than Euclidean distance in the case of the standard softmax loss. So the effect of these different training objectives is probably better understood just by looking at visualizations. So what I'm showing here to the left are embeddings resulting from using the softmax loss, and to the right from optimizing the angular margin loss. So you can see that the clumps are much better separated to the right, which is the effect of that additional margin term. And just to give a little more detail about how these figures were produced, each point is the result of an embedding of an episode of 16 contiguous Reddit posts. I'll say more about data in a second. And then they were projected to R2 using t-SNE, where each color corresponds to a distinct author. And you can see that points of the same color tend to be grouped together, and that they're better separated in the case of the angular margin. Before going into experiments, I want to say a bit about the data. In the paper, we looked at 3 data sets: Twitter, Wikipedia, and Reddit. For this talk, I'll just focus on Reddit. We looked at 2 months. The first was for training, and then the next was for testing. By design, all the testing data is future to the training data. We kept users with at least 100 comments. This is to ensure that we have enough history for each of them. And each comment consists of the text, the publication time, and the subreddit, which is quite useful contextual information for the comment. For validation, we held out the last 25% of the training data. And as a final comment, the evaluation split has roughly 50% of users that are novel relative to the training set. So in the paper, we report a few different kinds of experiments. I'll first talk about ranking experiments. So to set these up, what we do is for each author, we assemble one query and one target episode. For each query, we sort all the targets according to increasing distance of the query. There'll only be a single correct target among all of these, and what we'd like to do is for it to show up at the top of the list. The position in the sorted list is called the rank. The median rank is the median of the ranks of all the queries. The mean reciprocal rank is similar, and the recall at k is a measure of the fraction of queries for which the target is in the top k results. Smaller is better for the median rank, and bigger is better for the mean reciprocal rank and recall at k. So here are the Reddit ranking results. These are over 25,000 queries, and each query is a ranking of over 100,000 candidates, and these are all test results. So you can see what we've done here is break it up into different types of features that are being considered. From top to bottom, text only, subreddit only, and a combination of all the features I mentioned before, namely text, subreddit, and the timestamp. So across each of these different types of features, the proposed method outperforms the baselines, and we say more about the baselines in the paper. What I'll say now is that they include both non-neural methods that just look at surface features such as character or word engrams, and we also include a recently proposed author classification method that we extended for our open world setting, and we extended it in 2 ways. The first was using our proposed training procedure by subsampling histories of user actions, and the second is to extend the architecture to include our final MLP projection that we found necessary to produce competitive embeddings. So we were pretty happy with these results. Overall, we see that the combination of all the different feature types produced rankings where the top candidate was often the correct one, even though we have over 100,000 candidates, which include novel authors that we haven't seen before. And all of this test data is future to our training data, which was from the month before. And so therefore it probably consists of a fair amount of topics that were not discussed in the previous month. So this shows that our embedding is resilient both to novel authors as well as novel topics. So the previous ranking experiments used a fixed episode length of 16. I wanted to quickly show this slide where we vary that episode length both at training and test time. And you see the expected trend, which is that as episode length decreases, it becomes harder to determine who the author of the episode is. The last experiment I'll mention is some clustering experiments we did on Reddit. So here what we're doing is rather than ranking candidate episodes according to a query, we instead produce embeddings of episodes by here 5,000 different authors with 5 episodes each, and then cluster these using an unsupervised algorithm into different groups. And here we happen to use affinity propagation in part because it doesn't require the number of clusters as an explicit input. So there are a few standard metrics that are used to evaluate clustering. I won't go into these here other than to say that bigger is better for all metrics, and they all lie in the range of 0 to 1. So we were happy to see that the results from the ranking experiments carried over to this slightly different task. So as an added bonus, we wanted to report on some work we've done since the paper was completed, which centers around the question of what the model is actually learning. So to look at this question, we looked at a method called axiomatic attribution, which very briefly is using gradient information in order to highlight important features. And we see some expected trends. So for example, some unusual punctuation, use of smileys is highlighted. We also see some less common spellings, for example, the British spelling of labor as opposed to the more typical on Reddit American spelling. We also see some kind of misspellings and curse words that are highlighted. So that concludes the experiments and this talk. So let me wrap up by mentioning some of the key contributions. Firstly, we tackled what we like to think of as a fundamental problem of learning to compare users on social media on the basis of what might be sparse evidence. We proposed a novel model and a training procedure using metric learning. We showed the importance of aggregating episodes of comments rather than considering single posts, and the importance of using both content, the text, as well as the metadata. So just a few closing remarks. Please get in touch if you have any questions or have ideas of directions to take this work in. The code and scripts to reproduce our main experiments are available online. Please go and use them. More experiments in the paper, I mentioned this earlier, both for Twitter and Wikipedia, and we think there are many exciting directions for future work. So some of them that we're thinking about are troll detection, maybe including bot detection, detecting compromised accounts, cross-platform author ID is another one, and there are many extensions to the model that we're thinking about, such as including social network features, image features on platforms like Instagram we think are quite important, as well as just simply scaling up our experiments. Okay, that's it. Thank you very much for your time.